Tavy said, we're some of, definitely not all of, because there are a huge number of us, and young scientists from the Deep Purple project. And we're going to talk a little bit today about kind of linkages between surface albedo and the physical and biogeochemical properties of the weathering crust. And our title says Greenland, but there will also be some non-Greenland stuff in here as well, just to keep you on your toes a little bit. And just to introduce yourselves, or introduce ourselves and introduce me. I'm Ian Stevens, I'm the first name on this list. We also have Lou, who's going to talk, Shunan is going to talk, and hopefully Joe, who's going to talk, if he manages to get into the meeting. But if not, we'll just deal with that as we have to. So first, a little bit of background just about our project and what we're doing as a whole. I'm sure you will kind of know a lot of these points already, that glaciers and ice sheets are kind of melting at an increasing rate because of climate change. And a lot of that is because we're seeing increasingly negative surface mass balances. And part of that is due to the expansion of bare ice areas. So you have an upward migration of the snowline, more bare ice exposed, so we get more melting, as well as some, obviously due to increased temperatures and so on and so forth. And over the last 20 years or so, we've seen the formation and the expansion of the dark zone on Greenland, which is a really visual, obvious example of this, which what this picture on the right here shows. And as these surfaces get darker, we get positive feedback, and that reduces albedo, drives more melting, and so on and so forth. And just to kind of support my claim a little bit that this dark zone has appeared in Greenland over the past 20 years, here's some work from Andrew Tedstone. And you can see up here in 2000, we don't really see a particularly large dark area, which is shown in this red color. And as we progress through the 2000s into the 2010s, we get this lot more larger and more prevalent dark percentage of the ice sheet. We don't only see this in Greenland, we see this in other places in the world as well. Here's some data from Switzerland. Again, this is not ours. You can follow up the citation. We basically see reducing albedos on glacier surfaces across Switzerland over the last 20 to 25 years. So what's kind of driving this process? And that's kind of what our project is really about. We know that albedo is controlled by light absorbing impurities, which is what this LAP's acronym is, that will probably appear quite a lot in this presentation, such as glacier ice algae, which are these guys over here. So we have two different types. Don't worry too much about the types, just know that there are two. And we also have other particulates as well, so mineral particles and black carbon. We also have the ice surface itself, which obviously changes, and we talk quite a lot about that in detail, which also controls the albedo. And those are the kind of areas we're focusing on. So as Tavy said, you've heard about the Deep Purple project before. So you've heard some things about it, and maybe you know what it's all about. And our main project question is what controls algal blooms and biological darkening? However, our project is divided up into 3 different working groups that will kind of work together, but do also have their own distinct areas. And we're all from the Weathering Crust group, which is Martin Tranter's group, whose name you've heard already. And we kind of focus on 4 sort of areas of this biological darkening processes, or just darkening processes. The first one is processes of the near surface ice itself. So how the ice changes in terms of its structure and architecture. We also look at the optical properties of these light absorbing impurities which are on the surface. And we have some modeling approaches to investigate that a little more and try and predict a few things. And then we take this point data and we try to upscale it across the ice sheet using remote sensing approaches. So for those of you who are kind of been paying attention to the numbers here, there are 4 of us and there are 4 sections, so you can probably work out how this is going to play out. I'm going to talk a little bit about near surface ice processes. Lou's going to talk a lot about optical properties. Hopefully Joe will talk a little bit about some of our modeling approaches. And then Shunan's going to talk a little bit about our remote sensing approaches. So I said it wouldn't just be Greenland, and it's not just Greenland. So I'm going to quickly just run through some of the areas I'm going to talk about. And some of the areas our project that we're working on currently has focused on. So I've done a whole bunch of work in Svalbard, up in here in Canada, some stuff in Greenland that's not Deep Purple, stuff up in Sweden, and a whole bunch of stuff in the Alps. We've also got these 2 Deep Purple sites. So there's this one down here, which I will call Greenland Narsarsuaq, because it's easier to separate them that way. And and that's located on the very southern tip of the ice sheet, and that's where we went in 2021 and in 2020. And I'll also talk about this other site up in the Lulasat, which is where we were in the summer of 2022, just to provide a little bit of locational context. So I said I was going to talk about ice surface processes. So I'm going to talk a lot about ice surface processes and introduce this idea of the weathering crust, which is a term some of you might be familiar with. Oh, Joe's made it. He's in. A term some of you might be familiar with, but not necessarily a term everybody might be familiar with, and definitely not as familiar with as I would like people to be with it. And we're going to start off by talking about what weathering crust actually is, because I think sometimes it's a little bit confused as to what this near surface layer actually does and how do we define it. First thing to kind of note, it's ubiquitous in the bare ice area. If there's bare ice, we find some form of weathering crust. Even if it's millimeter scale, you still find it there. And it's basically a near surface layer of degraded ice. So it's formed by light entering the subsurface. Ice is obviously translucent, so light can get underneath the surface itself and cause melting underneath. And theoretically, this layer can be up to 2 meters deep. And what we actually see in practice is slightly different, but we'll come to that when we have some data later. But the main point here is that we have this sort of shallow near surface layer that's characterized by a reduced density. We've had internal melting and rotting of the ice surface. So if we compare it to conventional glacier ice, the bulk density is far lower. You might also see it referred to as the WC or the WCA in the literature. And just to be super clear here and make a very childish joke, we're talking about this area on the ice surface, not this section underneath here, which some LPIs like to refer to it as. So we know we have this layer. How does it happen? What does it mean? What does it do? And to start off, we're going to talk a little bit about some of the ideas we have about how the weathering crust forms. And we should kind of know at this stage that this is kind of qualitative or based on physical theory rather than any sort of empirical measurements. So a lot of the numbers you will see at this stage of this presentation are kind of ideological rather than being based on any actual, any actual stuff that we've measured. So as I've mentioned, shortwave radiation penetrates into the near surface of the glacier and it causes melting of the subsurface. And that melting occurs along the boundaries of the ice crystals, making them smaller and increasing the void spaces in between them, which is what reduces the bulk density of the ice. So if we have nice sunny conditions, we have really high incident radiation. Incident radiation provides a big proportion of our melt energy. We get lots of penetration to depth, and we really rot our ice, really enlarges void spaces and reduce our bulk density. Now, shortwave radiation doesn't penetrate the surface, and the receipt doesn't decrease in a linear manner. It's a non-linear decrease in receipt of radiation, which you can see here. Again, remember these are idealized. So at the surface, we get for super clear crystal ice, all of our incident radiation hits the surface. Some is reflected, some is absorbed, some penetrates. And as we move down the depth profile, the same process goes on and on. We get this non-linear relationship. And what that means is we expect to see a non-linear decrease in, or increase, sorry, in density with depth. So at the very surface, we expect to see the lowest densities. At the base of the weathering crust, we expect to see the highest densities. And then the base of our weathering crust is obviously defined by our unweathered meteoric glacier ice. So that's where our densities can be the highest, so 910, 920 kilograms per meter cubed. And so we have really nice sunny conditions. We have super high radiation receipt relatively. We get a very weathered, very degraded surface. When we have kind of more cloudy or darker meteorological conditions, our radiation input drops, and we expect to see the weathering crust to thin relatively. We're going to have some surface lowering. And then, I can't actually see my slides because the Zoom link is over the top, so bear with me, much better. And then when we get really kind of cloudy conditions or really dark conditions, our incident radiation value drops right down. The turbulent fluxes become a lot more important, and our weathered surface of really low density ice gets degraded or gets lowered. These are very exaggerated cartoons. And we get kind of clear blue approaching meteoric glacier ice. So we lose a lot of that really low density ice. And that's basically because the turbulent fluxes become a more important component of the melt energy supply. Our surface lowering rate exceeds the rate the weathering crust is formed and ice is being degraded, and the weathering crust itself thins down. So we have a bit of a mechanism there. And this is all going on all the time. We have a very kind of dynamic system where we have, if we have a sort of period of sunny days, we have weathering crust formation in the day, and then that slows down overnight, speeds up in the day, slows down overnight. And in different areas, we have different radiation receipts, so that goes on at a different rate. We suspect, anyway. And this is not just a dry system. We also have a lot of water moving around within there. So I've created the impression so far that we make these voids between ice spaces and we fill them up with air. And in fact, actually meltwater can drain down into these. So anything that's produced on the surface or in the subsurface will initially fill up in these void spaces. And that water will drain downwards until it hits sort of a water table. And it can't drain down any further because we have an aquiclude at the base of the weathering crust. We have this non-weathered glacial ice, which is essentially impermeable. It's about the same permeability or porosity as a granite. So for all intents and purposes, it's completely impermeable. And then we end up with this perched aquifer. Now in this aquifer, our water table can be anywhere between the surface or around 45 centimeters deep from the surface. And then it will move up and down as meltwater is supplied in and meltwater is drained out. And what we're going to do now is have a quick look at a little bit of data from that. So this is from 2021 in the southern tip of Greenland. And we basically had five probes sitting on the ice surface measuring the water table depth in these holes. So along the bottom, you can see day of year, and on the y-axis up the side, we can see the water table depth. 0 is at the top because it's the surface, so it makes sense that way around to me. And we have 40 centimeters at the bottom. And got a bit of mess here with this green line. I wouldn't focus too much on that. But the key thing to pick out here is that we have kind of a fluctuation in the water table. It moves up and it moves down throughout the day and throughout the night. Should also note that during this period and this field campaign in general, we had very, how to put this, unpleasant antecedent weather conditions. It rained a lot. We had a lot of cloud cover. So we don't really see a very nice diurnal cycle in here because of that. Yeah, so those are kind of the key points I want to pick out here, basically. Our water table is between sort of 0 and 15 centimeters normally, can be as deep as 40 centimeters. And while this number looks really high, I did actually validate it by looking at the hole, which was empty at that point in time. So yeah, we have this up and down water table. But on top of that, the weathering crust is part of the supraglacial hydrological system. It's a really underappreciated part. A lot of people kind of ignore it and don't really worry about it, but I'm going to try and sell to you why it's really, really important. So we have this saturated layer of ice, and within that, it's full of water, obviously, because it's saturated, and that water can move around. It's driven by the same forces we see in groundwater and the soil, and it fulfills a very similar role in the supraglacial hydrological system as a soil would do in a terrestrial system. We don't just have runoff straight over the surface, we have subsurface water flow. And there's a few kind of measurements we're going to introduce here. So I've talked about this density curve already. And what we expect to see alongside that is a porosity curve and a hydraulic conductivity curve, where less dense ice is more porous, so it's more hydrologically conductive. Water can move through it more easily. And denser ice is less porous and less hydrologically conductive. So we set out to measure some of this, and a large amount of this was done on a lot of these kind of spread around the world sites that I was mentioning earlier. And what we basically found out is that our mean hydraulic conductivity was 0.185 meters per day. And that's about the same as a sandstone. What we can see here is we do have some kind of quite large measurements, but generally we're talking in the order of magnitude between sort of 0.1 and 1.0. And we did see a little bit of regional variation, but that is not actually due to any kind of true regional variation. Some of it is an artifact of sampling season and study site selection just being slightly different. And what we actually don't see in any of this is any statistical difference. Even though these bar charts look kind of different, we don't actually see any difference in between our sites statistically. But to bring this back a little bit, I can go back. when we're measuring this hydraulic conductivity, I talked about this potential depth profile. We're only measuring it across the entire depth profile. So this is an average from the highest point to the lowest point within our weathering crust. And basically, we didn't really find a key control. So we measured a few other things. Surface slope was one of them. Antecedent metadata was one of them. But the key kind of driver of hydraulic conductivity was our water table height, with higher water tables being more hydrologically conductive, which fits in really nicely with this profile you would expect to see. If our water table is up into our nice, fluffy, undense ice, we're going to have water moving more quickly. And if our water table is really low, our porosity is really low, our density is really high, we're going to have water moving more slowly. And so our kind of next step for that is to look in more detail at how the ice itself is changing within this and trying to measure velocities at given depth. And the key point of this basically is that the weathering crust is delaying water transfer through the network and is providing a residence time for water in the near surface of the glacier that's really potentially productive for biological organisms and for biogeochemical cycles. And as we kind of talked about, this layer receives light, so it's got water and it's got light, so in theory, things can live within there. Which we'll come back to in a second. So what these hydraulic conductivity measurements imply is that we have a water flux in the order of kind of 10 to the minus 2 meters per day. And that's a velocity, and that's based on hydraulic conductivity and kind of modeled porosity and distance between our sample sites and the nearest stream and the surface gradient and the subsurface hydrological gradient. And we see that in the Alps. So we went to Vadrac del Forno, or I went to Vadrac del Forno in 2016, and we got this number. And there was a bunch of work done at S6 in 2014, where they also got a similar kind of number. And what that basically means is we have a period of water storage going on in the near surface. And even though, so at the Swiss site, we saw a delay between peak melt and peak stream discharge of 47 minutes, implies the weathering crust is moving quite quickly. This water flux value doesn't really line up with that. Instead, that implies we sort of have a 20 to 60 day water storage period based on those flow path lengths. And the implication of that is that we have displacement flow going on with the weathering crust. So melt water is added in, the water table goes up, water flows through, and water that's been stored in the crust is driven out into the streams, and the whole system kind of shunts its way along. And we call that displacement flow, which then obviously, as I kind of said, skipped ahead of my slides there anyway, provides time for biogeochemical cycles to occur. And just to exemplify this again, this is some work I did in 2021 on Greenland, where we measured a whole bunch of hydrology. We also had water table depth, stream depth, a surface elevation model, and that allowed us to construct a water table. We had some density measurements, which allowed us to construct porosity measurements, and basically come up with a flow path using some hydrological models. And then this is just one example we picked. So we took this hole here, which we call D, really imaginatively. And we're actually trying to look at some hydrochemistry stuff, but the key crux for this presentation is that, again, we kind of see this 10-day residence time within the weathering crust, theoretically, for water to move from a point into a stream. And this is over kind of a few meters scale, as you can see from the scale bar on here. So we have this water, it's in the weathering crust for a long time, and there's potential for stuff to live in it. And, for those of you familiar with deep purple, you probably have heard this already. And we have a few different microbial habitats within the weathering crust. The first one of those is the surface itself, which is where we find our ice algae, which we can hear a lot more about later on. But we also have microbes living in the subsurface. So we have bacteria and cyanobacteria, potentially bound to crystals, potentially in the meltwater, both in the unsaturated layer and in the saturated layer of the weathering crust. And then we also have cryocona holes, which I'm sure we're all kind of familiar with these microbe mineral aggregates, which are, I should actually add before I skip ahead, hydrologically connected to the rest of the weathering crust. So this stuff's living in here, this is what's moving around. Let's kind of have a look at how the two interplay. And again, we're going to go back to a big kind of Northern Hemisphere wide study where we're to the Alps, Svalbard, to Canada, to Greenland. And we found pretty much everywhere we have 10 to the 4 cells per milliliter in surface meltwater. We find it in the weathering crust meltwater, we find it in streams, and it's a pretty similar number to the one we see on the surface. And the implication is that microbes are mobilized through the weathering crust. Once they get into the weathering crust meltwater, they drain out through and they end up in the streams. And again, we don't really see any particularly large spatial variation. Again, any kind of difference between the box plots here are non-statistically significant. But what we do have is a few kind of questions about this. We don't know where these microbes come from. We think we know where they go. And we don't know whether it's viable microbes which are moving around or whether they're just retained on the surface. So that's always, we have some more work to do. But what we did do is we had a look at what controls these particles moving around, because for the intents and purposes of albedo, all of this is a light absorbing particle, even though they have different properties. We don't really see any clear controls on transport. So we had a look at hydraulic conductivity, which is on the bottom of these middle graphs, and cells. As you can see, this is probably the most upsetting scatter plot I've ever made in my life. I was really upset the day I made this. We also have the same thing for stream discharge. There's no clear links there at all. But what we do see is that microbes and non-microbial particles, so sediment particles, are mobilized under the same conditions. So we're not entirely sure whether that's just because they're mobilized under the same conditions or because there's some kind of process-based association, whether the microbes are bound to the sediments or whether they're scattering the nutrients from the sediments. We're not too sure, but we do know they're mobilized under similar conditions. And then we kind of promised you some biogeochemistry in the title. This is as biogeochemistry as we're going to get. And what we did with all these cell numbers is, if they're being exported efficiently, is we assumed that they are going to end up in the subglacial network and the proglacial network. And we could think of all these cells as packages of carbon, tiny little particulate organic carbon is the term. So we took our concentrations, we took a melt model, we multiplied the two together, and we predicted very boldly how much carbon glacier surfaces are going to deliver downstream over the next 80 years. So the numbers I've got here are from the middle scenario, RCP 4.5, which is in this plot here. We basically get 2.9 times 10 to the 22 cells per year, which means nothing to anybody because it's a giant number, which is equivalent to 0.65 million tons of cellular carbon, which is around about 15% of the total export carbon from glaciers, with the rest being sourced subglacially. When we compare with kind of some work from other studies that suggest particular organic carbon for glacier surfaces, our numbers align very well with their numbers, suggesting a lot of that material is actually cellular in nature. And I should also caveat this: when I say glacier surfaces, we're only really comfortable upscaling to regions we'd sampled or regions that were similar to the ones we'd sampled. So we stuck to the RGI regions 1 to 12 and Greenland, where we'd sampled directly. So this number is actually a little bit of an underestimate because we've missed off quite a lot of the Southern Hemisphere and Antarctica, obviously. The other kind of thing to note here is there's a huge amount of regional variation, but that's all connected with regional changes in glacier mass and glacier runoff itself, rather than any kind of cellular biological changes. There's a paper on this coming out soon if you want to read more about it. So I've talked quite a lot about the weathering crust. The title was albedo, so it's only kind of fair to bring this back around and sell you some albedo. And what this basically means for the albedo of the ice surface is that we have a very dynamic environment. The albedo, as I said, is affected by the ice architecture, which itself is changing as the weathering crust responds to meteorological conditions. It's affected by the microbes that live on and within the surface. It's affected by the other particles that live on or are on and within the surface. And it's affected by the hydrology. A key part of that is the water table, which we'll move on to talk about a little bit better. And basically, we need to understand what's going on in the subsurface and on the surface a little bit better. And the surface, actually, we have a good handle on what's going on the surface. And we have developed a model which does a lot of that, which hopefully, if Joe is here, Joe will be able to talk about. Are you here, Joe? not a good silence. Okay, well, hopefully,
I can take over if you want.
Hopefully, Lou will talk about it. Thank you,
Lou. Yeah, so in order to look at the different processes that are impacting on the surface albedo, we're working with the radiative transfer model. Biosnicar is a fully open source radiative transfer model, and it's the direct translation of the Snicar model that was written on MATLAB. And it has some additional features that we've been working on, and in particular, it's been thought to be applied to Greenland's ablation zone. So I'm going to talk about the specificity of this model a bit afterwards. We've developed a web app, so you can use the model directly from the link that's indicated on this slide. But you can also use it from, next slide please, Ian, from downloading the Biosnicar package directly from GitHub, where you'll find a file with the different input parameters to fill in, and then you can just run the driver directly from your terminal. You also don't need to configure any environment if you use VS Code, as there's a pre-configured dev container included. We've also been working a lot on validation and error messages, so the model is designed to be user-friendly. And there's also, we've also been working on the documentation of the model, which is the next slide, please, Ian. So that's, it's easier to navigate the different options that you have with Biosnicar. Biosnicar is a plain parallel two-stream model, so it means that it cannot represent directional reflectance. And we also are still in the process of constraining the different parameter spaces to apply to the Greenland's ablation area. You can go to the next slide, please, Ian. The next one. And so from a modeling perspective, when we look at the weathering crust environment, what we are interested in is the properties of the ice, as well as the physical properties, as well as the hydrology that are going to impact on the surface albedo, but also different absorbent particulates that are present at the surface, which include algal cells, mineral dust, but also cryogenic granules that can be dispersed on the crust from holes melting out. And all these components will create a very different spectral signature. Next slide, please, Ian. For example, a surface that's colonized by an algal bloom will have a specific signature in the visible spectrum like this, and in particular with this chlorophyll bump at 675. Next slide, please, Ian. A surface that's where you have dispersed cryogenic will have pretty much a similar impact as black carbon on snow, so it will just reduce the albedo over pretty much the whole spectral range. And then, next slide, please, Ian. Another very important component is the changing ice structures, as Ian was mentioning. So on the two first pictures, you can see that the way the surface looks, the surface can change quite drastically from a completely waterlogged surface to this porous crust that's developing and looking white because of the many scattering interfaces that are being created from the weathering process. And the plot that you can see just below is the surface reflectance of this very white porous surface on the solid line, that's represented by the solid line. And then when we strip that crust away, which is the picture on the right, you can see that the reflectance drops quite a lot. So this process of growth, crust, and decay is actually very important in driving the surface albedo. So what we have started to focus on with Biosnicar is to incorporate algal cells into the model because it's been shown that the blooms of algal cells are significantly contributing to the darkening of the western margin. And what we were missing in Biosnicar was were optical properties for these cells to be able to model blooms. And so what we've been doing, we've been measuring these properties. Next slide, please, Ian. That you can now soon see on the screen. With again the chlorophyll bump at 675, and we incorporated that into Biosnicar, and then we used the model in inverse mode to try and reproduce reflectance spectra that we collected in at the southern site of Greenland. Next slide, Ian. And the plot at the bottom of the slide now shows an example of one of these reconstruction that we've been doing, and we found that the model is now pretty good at reproducing the spectral signature of a surface that is colonized by an algal bloom. However, using these reconstruction, we assume that the only light absorbing particulates that are impacting on the surface reflectance are only algae. And so the next step was to look into the mineral dust. Next slide, Ian. So we've been doing the same work with mineral, trying to measure the optical properties and incorporate that into Biosnicar. And this is preliminary work for now, but typically what we basically what we observe is that we are improving the fit between the model and the empirical data that we gathered in Greenland when we incorporate this mineral dust into the model. Next slide, Ian, please. Yes. So you can see to the left is only when we add algae, and then to the right is when we incorporate dust as well. So this corroborates previous results that show that dust is not significantly, at least the dust that's associated with algal blooms is not significantly impacting the albedo or it is darkening the surface, but rather almost in this case increasing it. An important thing that we haven't been working on yet are the cryoconnect granules, and they are the inverse method that we've been working on doesn't work on with cryoconnect granules for the simple reason that they impact the spectral, the whole spectral range, so we cannot really isolate the signature. Typically, we can reproduce the impact of cryoconnect from like increasing the density in the model, for example. And the last component that I haven't been talking about yet is this eye structure. We are still trying to, we are now trying to validate the Biosnicar with empirical measurement of the weathering crust, like physical properties that Ian will talk about just after. And this is very important because, as we've seen, the changes in the ice crust are driving the spectral signal quite importantly. So once we have this validation of the model with empirical data, then we can start building a weathering crust model that will give us insight into how this crust is responding to meteorological parameters and how the albedo is changing from on like hourly to daily or even seasonally time scales. And the final goal with this is to incorporate the light absorbing particulate into that model to look into the feedbacks between them. And if you look at the picture at the bottom of the slide, you can see that it's quite obvious that the particulates are sort of compacting the eye, so they're almost, or it looks like they're preventing the crust from growing, and so that's the kind of feedback that we also want to look into to understand better the indirect role of the light absorbing particulates, and in particular indirect role of the algal blooms on the surface albedo.
Back to me. Okay, cool. Yes, as you said, we've been trying to just roll back, measure some of these empirical weathering crust properties, and the main way we've been trying to do that is measure the density. So I've talked about this characteristic depth density profile we expect to see, but just to remind you that it exists. And we expect that to link to the weather conditions. But like we've said, we're lacking any actual real measurements of this. And we started off having a go at this in 2019 with a kind of proof of concept study, which we did in Svalbard, which, as you can see from this picture here, was an incredibly high-tech method using this technical carrier bag and a luggage scale. So we had quite poor resolution of measurements. And we were actually picking out our depth profiles by taking a shallow core, pulling out the ice, and then recoring the hole a little bit deeper. However, we did actually get some kind of data that showed us we did have some change in density with depth, so we weren't completely on the wrong page. So again, we can see depth on the y-axis here, density on the x-axis. We have increased density with increased depth, as we kind of expect to see, apart from a few of these kind of weird and wonderful points here. However, this method is obviously kind of a little bit village, so we moved on to a slightly improved or heavily improved method from this carrier bag and luggage scale. So what we did was we collected our ice core, took it out in one piece, sliced it up, drained each of those segments of water to make sure we were actually measuring ice, not ice and water mixed. Then we put it in a bag, which was pre-weighed, and then we weighed it on a lab scale. So we actually had the worst resolution we had was 0.1 grams. The best resolution for some thin slices were 0.01 grams. And the only reason for the differences there were because of the weighing limits of the balances we were using. But that gave us a far tighter way of constraining density. And here's some data from that. So the different sort of facets here with different numbers on are simply just days of year to make it slightly easier to look at. And this, again, as with the kind of other data from 2021, there's no kind of overriding meteorological conditions apart from cloud and rain. There was some sunshine, otherwise we would have had a weathering crust, but there was not a very kind of characteristic flux or change of radiation. But what we basically see is we do have weathering crust forming, and we do see this kind of low density ice at the surface, higher density ice lower down, and if you kind of squint a bit, and on quite a lot of the lines you have a non-linear trend. And I mentioned at the start we have this theoretical 2 meter limit on the weathering crust. And what we actually see, or what we saw in 2021, is the base of the weathering crust was never anything more than about 50 centimeters. And we defined the base of the weathering crust as sort of that meteoric glacier ice, so density of 917 kilograms per meter cubed, which is what this dashed vertical line is. And obviously dashed horizontal line is where our base of our weathering crust crudely is. And if we just have a look at that against our idealized graph, we see something kind of similar. So that's quite nice for us. So we've got some measurements to start to constrain this a little bit. We then went a step further in 2022, and we tried to reset the weathering crust and measure its formation from meteoric glacier ice to degraded weathered ice. And what we did is we cleared a whole bunch of ice off the surface, which this video of Lou is showing. We used some really high-tech equipment, as you can see. And then we covered the surface with solar panels. And the idea of that was to basically reduce the receipt of radiative fluxes to the ice surface and sort of promote the importance of the turbulent fluxes. So if you think back to the very start, we're kind of working with this idea that radiative fluxes are driving our weathering crust formation, turbulent fluxes are degrading or lowering our weathering crust. We wanted to basically reduce it as much as possible. And we left that covered for 3 days with solar panels. And the reason we picked solar panels is firstly because they're designed to absorb radiative fluxes. So they're actually quite good at it, and also just because we had some hanging around. So we then uncovered it, and then we measured density, we measured reflectance spectra, and we collected metadata at the site for a period of just under 24 hours, I think it was, with a reasonably high frequency during the day. And I should add that we assumed that in this square we cleared, which the scale was about 2 meters by 2 meters, that all of our ice was identical. So we're sort of recoring at different sites through this square. And we made sure there's no coraconite and no very obvious debris, no very obvious structure that we could see, and we're assuming that this is all basically the same. So here's some more density profiles. So when we uncovered our ice, it was about 10 in the morning. And by the time we'd sorted ourselves out, taken some measurements and drilled our first core, we're on to 10:35. And we're super pleased with what we saw. So we have that ice, which is just over 900 kilograms per meter cubed. So we're really, really happy that we'd managed to kind of reset the weathering crust, and we were hopefully going to measure it forming. And what we can see here is we progress through our time steps. So the numbers at the top are the time of day. The numbers on the top of the facets are minutes since the start of the experiment. And we can see we're starting to get a density curve forming. Or it's starting to get that characteristic weathering crust forming as we go through the day. And then we carried on. So we did some cores at 5 p.m., 8 p.m., did a midnight core. As you can see, this wasn't our finest core, but there we go. And we did another core the next morning. And again, we kind of have this characteristic density profile. But we can see by this 8:45 one that once you've had a whole night, and I should add that we did this in August, so we did actually have darkness for a few hours, definitely kind of nautical twilight for a few hours, and there's some data coming up to support this. We do see a kind of reduction in this, or increase in the surface density and a reduction of the level of formation of our weathering crust. And to kind of sum all this up, I've just taken the density of the top slices. So this is around 25 millimeters from the surface to the subsurface. There's not exactly 25 millimeters every time, but we're in the kind of plus minus 3 millimeter ballpark. And what we see at the start of our experiment, our top slices, as we kind of said already, 900 kilograms per meter cubed, and that density reduces throughout the day. And we kind of see this increase into our midnight measurement and our next day measurement. And on our right here, we have our net solar radiation during that time. So this is measured using two semi-hemispheric pyranometers, one pointing up, one pointing down. One minus the other gives us our net. We can see we have this kind of big radiation peak towards the middle of the day when our weathering crust is degrading really nicely. And as our solar radiation receipt drops, our weathering crust formation slows and then starts to reverse a little bit. And as I promised, it gets dark and we have this period of no radiation receipt essentially overnight. And all that's gone on here is we had a few clouds coming across the sky. So we've got this kind of formation pattern that we expect to see. What does this mean for the albedo? Well, we have some detail first, so skip ahead. And we're just going to focus a little bit on these daytime measurements, so between 10:30 and 16:20. And that's because it's when we could reliably collect reflectance spectra. And for various reasons, which Lou can answer if you're so interested. And like I said, we've got this density decrease, and this is kind of a visualization of the change in surfaces. So as you can see, our kind of mission to get debris-free ice did not completely succeed. There's a whole bunch of tiny little cryoconites in here. The scale of this yellow arrow at the top is 50 centimeters on each edge. And we also have this little bit of structure in here. But you can see we kind of go from this sort of shiny blue ice to kind of white and fluffy ice. And what we also see over this time is a change in the broadband reflectance. So we kind of start off around an albedo of 0.51 and a bit. And that slowly increases over time as our density decreases. And I'm sure what you kind of are expecting to see here is exactly what you are going to see. But first, as a caveat, this relationship is only for bare ice. I'm aware there are a lot of small cryoconite holes here, but we're going to assume what we have is as close to bare ice as possible. So that's no particles, no algae, no nothing. We do kind of see that the density of our top slice does align with our albedo nicely. We do have this sort of predictive relationship. And we have this really nice high R-squared value, like 0.87, really nice low p-value for this relationship, but we do only have 7 samples. So that's always something that we want to be a little bit wary of. This is very preliminary data. I'm not presenting this as this is the way to predict, but it does kind of show that we are making some measurements and we're onto the kind of right thing. We just want to expand that number of measurements we have to really inform our modeling approaches. So let's skip ahead. So I've talked quite a lot, and Lou's talked quite a lot about what we're doing at a very local scale. And now we're going to move on to Shunan, who's going to talk a little bit about how we're trying to upscale our efforts and use remote sensing to explore these processes in far greater space than the small field sites we've been focusing on so far. So over to you, Shunan.
Yeah, thank you, Ian. And hello, everyone. I will talk very briefly about the remote sensing component of the Deep Purple project. So as you have probably heard it before, and also you can see it in this figure on the screen, On the southwestern part of the Greenland Ice Sheet, there's a belt of ice with albedo that is significantly lower than the surrounding ice. And that area is known as the dark zone. And the darkening of the dark zone is driven by different biophysical process. And on the next slide, you can see one of the biophysical processing. Yes. And that is the growth of glacier algae, which lowers the albedo in the melt season. And in addition to the glacier algae and also the pigment they produce, there's also other light absorbing impurities, which you can see in the next slide. Yes, and you can see there's a quite complex, different type of light absorbing impurities, and there's also mineral dust. And our team has collected lots of field samples in the fieldwork. And the next slide, you can see a drone video. Our colleagues, Katie and Ed, who are collecting the samples from quite host in this year's fieldwork. And this helps us understand the biophysical process at the point scale. And we would like to understand this process at a larger scale using remote sensing data. Yes. And my part of the project focuses on upscaling the point scale process to the regional scale. And hopefully we can understand the spatial and temporal variation, the albedo and its driving forces, and the entire Greenland ice sheet. And on the next slide, I will show you briefly about the work packages. So basically, the remote sensing data we use are multispectral and hyperspectral satellite or drone data, and they are essentially multi-dimensional arrays. So my PhD study is basically finding a way to reduce the dimensions of the data and convert them to meaningful biophysical parameters, such as albedo and the quantification of the glacier algae. And eventually, we want to figure out what's the relationship between the algae and the albedo. So basically, how much percentage of the albedo variation is contributed by the glacier algae. And on the next slide, I will show you one of the web apps that was deployed in the first work package. And so basically, we first use the statistical band-to-band analysis to cross-calibrate the Landsat and Sentinel-2 data sets and harmonize the satellite data to become consistent time series data, and then apply the narrow to broadband conversion algorithm to calculate the albedo. And on the next slide, I will show you how to use this web app. So basically, you can either scan the QR code on screen, and I will send the link to this web app in the chat later. So basically, you can just click on the map anywhere that's a point of interest, and you will see a time series of albedo in the chart. And you can also download the chart as CSV data. And also you can also just change the date in the button and try to load a natural color image and also the albedo in this web app. And if you zoom into a smaller area, then you can also get the albedo image and export it as a GeoTIFF format. And at this moment, this web app was only available to the Greenland Ice Sheet. And next week, I will be presenting the validation of the albedo outside the Greenland Ice Sheet in other Arctic and the glaciated areas. I will present this in the IGS Nordic Bunch meeting next week. Yeah, and thank you. And back to you, Ian.
Yeah, so back to me. And I'm just going to sum up now, basically, so you're not going to have to hear too much more from me. And I'll talk about a little bit about our next step. So it talks about how we think the weathering crust forms, how it degrades, and we presented a little bit of preliminary data for that. And our next step is kind of really tie that down and link it with albedo, kind of more formally than we have already, and incorporate that into our modeling approaches. And we also talked a little bit about controls on water and particle flux in the weathering crust. And I want to explore how that links with density and also try and measure that throughout the depth profile. So rather than taking an average of the whole weathering crust, we want to look at specific sections and see if we have different processes going on or areas of different importance, which is what we would kind of expect to see. And we also talked very briefly about biogeochemistry, as we kind of promised. And we have this sort of movement of particles from the surface to glacier streams and potentially downstream. But we want to sort of drill into that a little bit more and try and understand where these things are really coming from, where they're going to, are they moving as efficiently as we think they are, and how does that all tie back into albedo? We're also going to be doing some work on nutrients in this system, and trying to see if that controls the algae, which obviously then links back to albedo. And We have this Biosnicar web app, which is now super accessible and people can go and use, and definitely should go and use. And Lou's done a lot of work on characterizing the optical properties of these surface impurities to really start to drive that. But what we want to do is really integrate the physical ice process into this as well, which we obviously mentioned, and bringing in that kind of ice structure, drilling in a little bit more to kind of other particulates and cryoconite, and then the feedback processes between those things and the ice architecture of the crust itself, and how that all plays into albedo. But yeah, go and have a play around with this Biosnicar app. It's good, basically, and very easy to use. I hate coding. I'm not a coding person, and I managed to use it. So that's a good sign. We also have this albedo web app and the kind of harmonized remote sensing albedo stuff Shunan was just talking about. Again, go and have a play around with that and get some really potentially useful data. And the kind of next steps we've got there to develop and validate the algorithm a little more and overcome some kind of challenge of imbalanced density data. So things to do with clouds and saturated pixels and so on and so forth. Cool. So that's basically what we've been up to in our section of Deep Purple. There's also a next slide here, which Tevi asked me to add in for the next talks. I guess first you have questions for us. So I think, yeah, I'll pass back over to the host and you can coordinate.
Great. Thanks so much, everyone. That was really, really interesting. I'll open it up to any questions. If you have any questions, throw it in the chat box or raise your hand like we already have right here. So Stefan, we'll go to you.
Yeah, a question for Luann about the albedo modeling. You showed that adding algae to the ice dropped the albedo dramatically, and you added then mineral dust, and it didn't change much. And concluding that, which I think is correct, that the biggest effect on reducing albedo is from the algal growth. But you could, in the modeling, you could rearrange the order of what you did. Start with the clean ice, and then first add the dust, and the albedo will drop some, and then you add the algae, and it'll drop more. So you get a different answer about the relative importance of the two impurities, depending on the order that you do things. Have you tried that?
Yeah, so actually the inversion method has been applied only on the infrared part of the spectrum to retrieve the clean ice. And then when you put the mineral into the model at the concentrations that we measure them with the optical properties that we've been measuring, there's barely any impact. So we could start with minerals, but it wouldn't change the fact that they don't have any impact on the output of the model. And when we look at the signature of the signal that is now on the screen, that we compare that with the optical properties that we measure of the algae, we can see that there is a clear match between the different spectral features that we observe on the absorption spectra of the algae and the drop that we observe in the visible spectrum of the spectra that we collect from the surface. Does that answer your question?
Maybe. What was the let's see, the concentration or the gram? No, I don't know. The for the dust, what do you have a mass mixing ratio for this?
Yeah. From last year, it went up to like 4 grams per liter. It was quite high. Obviously, that is nuanced by the sampling techniques that we still are having struggled with, because it's quite complicated to sample bare ice properly compared to snow, where you can be much more precise with the depth. So it's a gram per liter on a very there's a quite big uncertainty on how deep we can sample. But the concentrations from last year were well, yeah, I think up until 4 grams per liter.
Thanks.
All right, we'll go to Roger.
Yeah, thanks very much. Thanks to all three of you for the talks. Question really for Ian. fairly near the beginning, you suggested you're pretty confident about the how uniform the depth is in the various places you've been sampling, and I can well imagine that's the case in nice open ice sheets and so on. But I've got vivid memories of working with Tavy and others in fairly narrow valleys where the amount of shade changes a lot during the day, and probably seasonally as well. So, how confident are you that the depth is pretty uniform across any given area?
Yeah, so I'm on the right slide, just so my brain is in the right place as well.
Yeah.
Okay, cool. So this is just very conceptual, and it's for an idealized unshaded piece of ice. And I very much agree with you that when you're working on valley glasses with shading from the side, that's going to play a very big local role in the system.
Mm-hmm.
And so far, all of the density measurements we have are from Greenland, and I think it would be nice to kind of expand that onto valley glasses. What we do have are all these hydrology measurements, which obviously I've kind of talked might link in with density, and we don't really see kind of the shaded areas as being any less hydraulically conductive in a systemic way than we do unshaded areas in the middle of the glaciers. And quite a lot of these glaciers are obviously valley glaciers. So we have Protected Bridge, there's a valley glacier in Svalbard, the Tongue of Fox fauna, again quite shaded. Store Glacier, Robots Glacier, again shaded, and all the alpine glaciers are very typical alpine glaciers. So I do kind of agree. I would expect to see very local scale variations in the Weathering Crust because of the shade. But what we have also seen from the work we did with the reset experiment is that it doesn't necessarily change on a kind of hour to 2 hourly basis with any massive rate. And that might be an effect of the fact we were sampling somewhere that was unshaded. But yeah, it's definitely something to consider for sure. Thank you.
Yeah, I mean, I've worked on Store Glacier, and I remember going in and out of the sunshine, during it. And of course, when you start showing density versus depth as a geophysicist, it immediately makes me think, can we find that out for you without anything invasive? And it'd be quite challenging for something that thin. So I'll annoy my tutees by asking them the question. Thank you very much.
Yeah,
cheers.
But to carry on from your point just there, we have thought about trying to use a radar. But obviously, the frequencies, you need a super high to measure something so thin.
Yeah,
and I'm not a geophysicist.
and anything where it's gradational like that, like you've measured as well as predicted, which is smashing. Where it's gradational like that, your analysis algorithms tend to be a little bit flustered from time to time.
Sure.
So good stuff. Thanks very much. Enjoyed it. Thank you, all three of you.
This time with my microphone not muted. Thanks so much, Roger. Any other questions before we wrap up here? Not seeing anything else. So I'd like to thank Ian, Luann, and Shunan for their presentation today. That was really, really great. I will note, if anyone is interested in going back on some details from this talk, it will be posted online on the IGS YouTube page and is available for subsequent viewing there. So I would encourage you to go back and rewatch the talk and follow up with the authors if you'd like. Thanks, Ian, for jumping to this slide. Next week, we're going back to sea ice, which is my bread and butter. That's my specialty that I bring to the cryosphere community. So like Ian mentioned, we have Dr. Letty Roach from Columbia, who's going to be presenting on Antarctic sea ice, and Dr. Kent Moore from the University of Toronto, who's going to be talking about some anomalous conditions in the Beaufort Sea during summer 2020-2021. So with that, we'll wrap it up. Thanks everyone for taking part, and we look forward to seeing you all again in the coming weeks as a part of this seminar series. Take care.
Thank you very much, everyone.